In this video, we are going to solve a linear algebra problem. This is a problem from CSIR NET June 2019 physical science paper actually. So the problem says the elements of a 3 cross 3 matrix A are the products of its row and column indices, which means the ijth entry is the number I times j. For ij equal to 1 to 3, 1, 2, 3. So this is a 3 cross 3 matrix, and one has to find the eigenvalues of this special matrix. So some options are given, 770, 743 and so on. So actually once we know the matrix, because we know the entries now, we can of course solve it for the eigenvalues. There is a lengthy process, but here we will not follow that process because this is a net problem, and there we use some trick. We will use some trick to solve that in just 30 seconds maybe. You can solve it in just 30 seconds once you know this trick. So okay, we know the matrix here. So the matrix A is 1 because this is 1 1 position, 1 2 position is 2, 1 3 position is 3, and similarly this is 2, this is 4, this is 6, and this is 3, this is 6, and this is 9. So we know the matrix now. One can of course solve this to find the eigenvalues, but we will not solve anything. We will just use some tricks. So first of all, it is very clear that the matrix is symmetric. This is the first observation. So this is actually symmetric. So the question is, what is the determinant of A? Can we just look at this matrix and tell what is the determinant of A? So let's write determinant of A, and then this is 1 2 3. Then I will write 2 common from the second row. So then again 1 2 3, and I will write 2 here outside, and then take 3 common from the third row. Again it is 1 2 3. So here 3 common. So this is this. So this is 6 times this determinant, but this determinant is 0 because there are identical rows. So determinant of A is actually 0. Now we know separately determinant of A is the product of its eigenvalues. But if determinant of A is 0 here, then one of the lambda i's must be 0, otherwise the product cannot be 0. So some lambda I equal to 0, which says at least one of the eigenvalues, one of the lambda i's must be 0. Then we go to the options. Let's check the options. We see that in this option there is no 0, so this cannot be the case. Similarly, in the second option we say that there is no 0, so this is also not a possibility because we know at least one 0 is there. So 0 is at least one eigenvalue of this matrix. So now it's clear that the eigenvalues will be of this form. So some number here, some number here, and then 0. We don't know who are they now at this moment. But here one observation we made here is that the matrix is symmetric. Now I will write an important fact like a theorem. This fact is very important in many situations, like in these exams, which is the diagonalizability, which means the symmetric matrix implies it is always diagonalizable. So it is clear now that since A is symmetric, A must be diagonalizable. So A will have some diagonal equivalent. So star, star, star. Suppose this is we can write this because A is diagonalizable. Since A is diagonalizable, there is a diagonal equivalent. There are some elements here, but we know which are these elements. These are actually eigenvalues, nothing else but eigenvalues, lambda 2, lambda 3. But again we know that at least one of them is 0, so make one of them 0. So write 0 here, but still we don't know what are lambda 1, lambda 2. Another fact is that rank of some matrix A is rank of the diagonal equivalent of A. So let's say D. This is also important. Capital R. So rank of A is rank of D, where D is the diagonal equivalent of A. So now if we find rank of A, we can get something. So our matrix is 1, 2, 3, 2, 4, 6 and 3, 6, 9. I will write A here. Actually these are very easy, straightforward to find, like rank, determinant, all these. You can just look at this matrix and find the rank and also the determinant. Here I will just write the matrix and find the rank. 2, 4, 6 and 3, 6, 9. If we do some row operation like R3 minus 3 R1 say, then what it becomes? 1, 2, 3, 2, 4, 6, and this becomes 0, 0, 0, 0. R3 minus 3 R1. Then again we put this operation, R2 minus 2 R1. So 1, 2, 3, R2 minus 2 R1, if you do, this will be 0, 0, 0, and this was 0, 0, 0. So it's clear that rank of A is 1. If rank of A is 1, then this diagonal matrix must have rank 1 by this. But if lambda 1 and lambda 2 both are non-zero, then the rank of D must be, so the rank of this matrix must be 2. But since rank of A is 1, rank of this matrix should be 1. So lambda 1 and lambda 2, only one of them can be non-zero. So one of them must be 0. So from the rank statement we get this of this form, like one of them is 0, you can make any of them. So lambda 1, 0, 0. So eigenvalue must be of this form. Now let's go to the problem, the actual problem. Here you see there are two non-zero elements here, so this is also not a possibility. So this is the correct answer. Actually, to solve this problem we have to use these tricks, and these are actually very standard fact. Also rank of A is equal to 1. We don't to find this we don't have to calculate anything. If we just look at the matrix, we see that other rows, second and third rows, just the constant multiple of some, actually the first row. So in these cases the rank A is well known to be 1. So this is how we could solve this problem. So now actually we have solved the problem, but again I have considered the same problem because I want to mention some other fact which is also very important in these cases, very important and very useful. So I'll write that fact now. So the fact is, the number of distinct non-zero eigenvalues of some matrix M. So number of distinct non-zero eigenvalues of some matrix M is less than equal to rank of M. This is actually a fact and very easy to remember once we know some examples, and it is very useful.